Hello everyone, this is Dr. Shane again, coming back at you with some more Chemistry 121 chemical bonding videos. So we're having some changes this week. This is week 3, and that's in quotes up there because we're going to be recycling some things or continuing some things from week 2 in all likelihood. So you can stay with the week 2 slides. I think it's slide number 16 that I'm starting with today. So you can see it's Roman numeral 3, Introduction to Bonding and Nomenclature. So if you want to spend some time before we get started to download those slides, unless you've already done so, set up that heading in your notes and actually just copy down all that stuff. Copy down all the basic definitions under letter A, and I'm going to chop this one up. So these videos should be a little shorter. We'll do bonding in this video and then nomenclature in the second video, and then I'll introduce the next big topic in the third one for week 3. Okay, so there's some announcements over there on the side, so we're going to finish the week 2 slides. With respect to homework, you always roll over problems from the previous week that we didn't get and put those on your homework for the following week. Also, this week we have that timeline activity, the brief history of atoms and atoms and matter. That'll be due as well. And believe it or not, we're actually going to look ahead a little bit to the exam. Just kind of think about it. I'll give you a checklist, and I'm making the exam a little earlier than normal so that we can get a good start. And as you see up there, I think the general consensus is that we do more of a flipped approach with the videos, make them shorter so it's not just another lecture that we do in class, and that we focus on the content here, and that you take the notes, the outline, the definitions that you're supposed to do right now under letter A, do that on your own so we don't have to take time in class. So before you come to class and we discuss Roman numeral 3, make sure you copy down all the stuff for letter A. I'll review it verbally, and then we'll go from there. So other announcements I'll give in class so that these videos aren't too long. Okay, so let's go ahead and get started, and I'll try to keep this to maybe about 15 minutes or so. Okay, folks, so here we are. I'm a little casual today. I just rode my bike up to the church. So here we are. We want to do the first piece of Roman numeral 3's introduction to chemical bonding and nomenclature, which is a fancy word for saying how do we name molecules. When we get to nomenclature, I'll remind you this later, there's a flow chart on D2L under week 3. You can print that out or at least have that handy. Flow chart for nomenclature. We'll use that in class to do a bunch of problems, but you won't be able to use that on a quiz or a test. More on that later. Okay, so the basic definitions, I think I'm just going to put these up here. Okay, so it's a pretty modest amount of content that I'm asking you to prepare. So it's just number 1 and number 2, chemical compounds, chemical bonds, and then the 2 major types of bonds, ionic bonds and covalent bonds. So let's just go through and write a few examples up here. So these are just examples, and I'm going to do, so you should do all of that. So copy that on your own. So have that all ready to go, and these are examples underneath them. So, some examples of compounds. So compounds are pure, if you remember from our hierarchy of matter. It's either pure or it's a mixture, and if it's pure, it's either an element, periodic table of the elements. We've discussed that at great length in previous videos. And then compounds, which are the way most things exist in the world. And what do I have here for the definition? They exist as molecules, which are combinations of elements bonded together in specific ratios. So let's use an example here, just 2 examples. So you might be familiar with those, so if you want to just take a second, what would you call those nomenclature-wise? Well, so I don't know if you know the names of these. Well, okay. I'm going to use more specific names kind of as a prelude to this. So this is water, of course. Or it's ice, or it's water vapor, depending if it's solid, liquid, or gas. I'm not too concerned about the state of matter right now. The technical name for this is dihydrogen. And you don't necessarily have to put the monoxide. Dihydrogen monoxide is 1. Or just dihydrogen oxide, when you don't write that, the 1 is understood. Okay. And this has a specific ratio of hydrogen to oxygen atoms of 2 to 1. Okay, that's an example of a compound. H2O2 is another compound that exists. This is actually called hydrogen peroxide, which you may have used on a cut or some kind of a wound, or with high concentration you can actually use hydrogen peroxide to bleach hair if you've done that. This is also, well, let's see, so that gives you the formal name. Okay, this is also a compound of hydrogen to oxygen, but it's a 2-to-2 ratio or a 1-to-1 ratio. So they're both made of hydrogen and oxygen, but they are different ratios. And we can't change these ratios. H2O is dihydrogen monoxide, H2O2 is hydrogen peroxide. Okay, so that's an example of compounds, and maybe that's specific ratios. Okay, types of bonding. All right, this is going to be quick, this is going to be nice. These videos are going to be much shorter. Okay, so those are examples of compounds. Excellent. Oh, it's also handy if you have your periodic tables. And I think on your periodic tables, we already put the dividing line between metals and nonmetals. It's that staircase that starts over by boron, goes down the side of boron, over, down. So if you don't have that, that's a really important dividing line. That's the dividing line between metals, which is the majority of the periodic table, and nonmetals. If you're not sure where that is, look it up in your book, Google it, and make sure that line is drawn on your periodic table, in addition to all the group numbers, 1 through 18. Alkali metals, group 1, alkali earth metals, group 2, transition metals in the beginning, boron group, carbon group, nitrogen group, oxygen group, and so forth. Halogens, group 17, noble gases, group 18. Make sure you have all that labeled and ready to go. Okay, so it says there under number 2, atoms bond together. The whole point of bonding, the whole ball game, if you will, is to make the atoms more stable than they are by themselves. That is an essential feature of chemical bonding, stability. To become stable, well, what does it mean to be stable chemically? Stable chemically means it behaves like a noble gas. What makes a noble gas stable? It has a full electron shell. The valence shell is full, all the core shells by definition are full. So it wants to mimic that stability. And there's 2 ways, primarily, there's a third, which we're not going to discuss too much. 2 ways that happens. And that's ionic bonding, and that's when a metal combines with a non-metal. And it doesn't have to just be one of each, one metal, one non-metal. It could be a metal and several non-metals, or it could be a polyatomic ion, which we're going to get into later. Multiple atoms making up the ion. It's a little more complicated than that. Or we have covalent, which if you think about it, it's cooperation between the valence electrons. And that's between non-metals. I just want to show you some examples here. Let's look at 2. Okay? Well, maybe 3. Yeah, we'll do 3. Yeah, 2, sorry. This is just supposed to be a director. I'm kind of figuring this out. Let's do something you already know. The nomenclature for this, you already know, this is sodium. You name the element chloride. This is ionic. We don't use the prefixes. We don't say monosodium monochloride for reasons I'll explain in a minute. Okay, so I think we did this already. Sodium is in group 1. If we didn't do this, so if we want to do a before picture, what do the atoms look like before, and what do they look like after? So that we go from unstable atoms to stable something, in this case ions. A positive ion is where you lose an electron, or one or more, and that's called a cation. And then a negative ion is one that takes those extra electrons and then fills its shell. Those are called anions. So let's look at, so sodium, you can go back and convince yourself of this. Sodium has 1 electron in its valence shell. So this is called the dot structure. It only shows the valence electrons. Group 1, 1 valence electron. Chlorine, I should use a different color, but I think you can do this since I'm doing this in real time. Has 7 valence electrons. And there's different ways of drawing this, but I like to do this. There's a good reason. 1, 2, 3, 4, 5, 6, and 7. So this is 1 valence electron away from being stable. 8 is a number to remember. It's not a universal number, but 8 is often a number that means something is stable. That's called the octet rule. We'll get to that one later as well. So what happens here is the metal loses the 1 valence electron. The non-metal gains, oops, let's stay consistent, 1 electron. So this is not really how it happens in nature, but it's a good way, it's a good thought experiment. So the electron goes over here, and then afterwards, sodium does not have its valence electron anymore, and chlorine now has 1 more. 7, 8. Excellent. Now they're both stable. That's awesome. But what actually holds these 2 atoms together? That's a bond, right? I mean, a bond means 2 things are held together. Well, the thing that actually holds them together is now sodium has a +1 charge. We don't typically write the 1 because it lost the electron and now the protons outnumber the electrons by 1. So get your head around that. You lose an electron and are left behind with a positive charge. The word lose often means, for a lot of you, associates with something being negative because it's math. You lose it, you subtract it. Well, yes, but it's a proton that outweighs it from the other end. Chlorine then will have a -1 charge. And if it's a positive charge, this is called a cation. This is called anion. And the ionic bond is the attraction, the electrostatic attraction between the plus and the minus. Fine. Please don't draw a line in between those 2. That means a covalent bond, so that matters, so don't do that. I'm just going to show you one other example kind of quickly. I think I can do this kind of before-after picture right here. Let's see. Magnesium oxide. We'll do some more complicated examples in class. Magnesium oxide is used in pigments. It's used in some sunscreens. And the before picture is magnesium has 2 valence electrons. Oxygen has 6. Group 16, 1, 2, 3, 4, 5, 6. And you see what's going to happen here. This is just going to happen twice. These 2 electrons are going to come over here. So we're going to have magnesium with no valence electrons and oxygen with 8. In this case, we're going to have a +2 charge, and you have to write the 2. That's really important. You don't just put plus minus, plus minus, plus minus, +1, +2, -2. I don't get too hung up on if you do -2 or 2 minus. I think -2 is the more accepted convention. I may be sloppy with that. And this is also an ionic bond. Okay, and we're just going to stick with those 2 for ionic. So ionic is a metal and a non-metal, opposite sides of the periodic table. And then there will be some other things here. Sometimes the ions are what are called polyatomic, which means they're made up of more than 1 atom. These are monatomic ions, 1 atom forming the ion. We'll get to that other stuff later. Covalent molecules are just between nonmetals, and I'll show you just 2 examples here, just simple ones. So let's do the simplest one of all. Hydrogen bonded to itself, diatomic. Well, let's just actually keep it very simple. Let's look at 2 diatomic molecules. And we're going to make this more complicated. This is an introductory video. So hydrogen, this is a good thing to know. Hydrogen is usually a non-metal, because on the periodic table it might be listed on the left side and the right side. It's kind of unique, but hydrogen usually behaves as a non-metal. Fluorine is certainly a non-metal, and you might recall there are certain things that are diatomic in their elemental form. Hydrogen, nitrogen, that's a different case, oxygen, and then all of the halogens. So H2, O2, N2, F2, Br2, and we'll do some more of those examples in class. So that's the idea. And if we wanted to do a before and after picture here, I'll try to do it this way. How about this? Hydrogen has one valence electron. The other one has one valence electron. We'll do them both. Why not? Fluorine has 7 valence electrons. And I guess I should probably write them both the same way. Although it's easier if I put the lone electron in the middle. That's all right. So what's the nature of the bond here? It doesn't make a whole lot of sense to simply take this electron and put it over here. It makes this one stable, but not this one. Well, that sort of does, actually. But this example down here, if I take an electron and just put it over there, it doesn't make this one stable. You actually lose stability if you do that. So what ends up happening is these actually share the electrons. How do we write that? Well, we actually write these 2 electrons are being shared, covalent, and we symbolize that by something you might remember. That's called a single covalent bond. 2 shared electrons. There are such things as double covalent bonds, triple covalent bonds, actually quadruple covalent bonds, which are pretty exotic. We'll get to double and triple bonds in class. So here, it's the same idea. It forms a single covalent bond, but all these other electrons are, let's see, I'm going to have to kind of shift these around, sorry. These are being shared. So those are being shared. And these other 6 electrons are not being shared, so they're remaining. But they're necessary for stability. These are called non-bonding electrons, sometimes called lone pairs. And I think that's enough. We'll do some other examples in class that are a little more sophisticated than this. But if you can come to class understanding the basic definitions of bonds, ionic and covalent, ionic is a metal and a non-metal, covalent are just non-metals, then we'll do more sophisticated examples in class. That's awesome. Let me just take a look at the notes here, and that should be just fine. Okay.